Hello everybody. Due to my absence and due to the complexity of the law of conservation of momentum, I've decided to do a little video blog for you guys so that you can see some of the pitfalls so that you don't make mistakes when you start doing the problems. So you will have seen a PDF file like this, I'm hoping, that states the law of conservation of momentum, all right there. And you've read through that hopefully, and so then you already know that for a system of objects where there are no external forces, the momentum of the objects before an interaction is equal to the momentum of the objects after the interaction. And we can see there in my note the reason for that is when the two objects come in contact with each other, they will be applying equal and opposite forces on each other due to Newton's third law. You can see force of 2 on 1 and force of 1 on 2. And that means that they will apply equal and opposite impulses on one another. And you'll notice there I've got the negative sign for the impulse there. Alright, don't forget that momentum is a vector quantity, and therefore the signs and the directions are very important when doing your momentum calculations. Alright? Also note when doing your calculations that we need a new notation to represent the final velocities, because now v1 and v2 represent the velocity of objects 1 and objects 2, and therefore we need to represent final velocities, and so we use that little tick up above the v. We call that prime, and that represents the final velocity. Alright? So, on the next page, you've already seen the fact that we can use those equal and opposite impulses to rearrange our equation and come up with what we call the conservation of momentum. The momentum of the objects before an interaction must be equal to the momentum of the objects after an interaction. All right? Now, before I show you a few quick demonstrations from my extensive physics equipment here at home, I'm going to just go over some of the questions to make sure that you get everything straight there as well. In question number 1 here, all right, and again you would have seen that, it's online. Be aware of, again, the signs for the direction. Our first object here is moving to the right, and therefore I gave it a positive sign for the velocity. Remember, these are all velocity vectors. And in velocity number 2, after the interaction, it is also moving to the right, so again I give it a positive sign in order to represent that. When we get our final answer down here, you can see that it is a negative sign for the velocity, and that represents that object number 1 is recoiling, heading back to the west, and that's due to the fact that object number 1 has a smaller mass than object number 2, despite the fact that I can't draw a picture to represent that. Alright, so again, be very careful with your vectors. You must take into account the sign when doing that particular type of question. Alright, very good. That first question was an example of what I would call a regular question. Both objects, one object is moving, or both objects could be moving beforehand, and both objects are moving afterwards. They're not sticking together, and they're not moving away. There's not an explosion in any case in those. In question number 2, we have a classic question that I would call a hit and stick problem, where the two objects move as one after the interaction, and there you can see there we can let velocity 1 prime and velocity 2 be equal, and therefore it makes the problem a little easier. And there you can see here my general equation for hit and stick problems, where those two masses are added together at the end. Again, make sure your signs are representing appropriate vectors. You can see here, and I'm trying to point to this, there we go. We've got a little negative sign right there representing the fact that the second vehicle was moving in the opposite direction. So again, make sure that you are using the appropriate situation there. Okay, and moving on to the last question. That is our explosion question, and you can see there that we have the objects together as one at the beginning, and therefore v1 equals v2, and in this case equals 0, and therefore we can put them together in the initial equation. It doesn't have to be the case that our two objects are moving with the speed of 0. We could have a hand grenade or something moving to the right, and then as it explodes, the pieces move away from each other as they continue to move. So be aware you can have questions that are explosion questions that also move initially. All right, so don't be afraid of that. All right, so that's the questions. I think they're pretty straightforward. Make sure you include the directions with those. Let's do a little demonstration here. We've got a couple of vehicles here, a fire truck, right? It's got a big heavy fire truck, and here we've got the poor bus, and it's not quite as heavy as the first. And I can simulate that first problem that we did by having the bus run into the back of the fire truck. And so my fire truck is initially at rest, my bus is going to be moving, the bus is lighter than the fire truck, and if you look very carefully, we will see that bus recoil back after the collision takes place. So here we go, we can see that going boom, and you can see there was a little tiny recoil. It doesn't roll back nicely. The wheels on the bottom of my bus here are not quite as good as my expensive carts that we've seen with the experiment. But I'll do that again, boom, and you can see it recoiled back and the bus continued on. But notice the bus continued with a much slower velocity. All right, so we've got some momentum transfer. But again, the momentum before with the moving bus is equal to the total momentum afterwards. If I switch the positions of the bus and the fire truck, then we will see that a different situation takes place. That fire truck, when it hits, will transfer some momentum to the bus and it will move ahead, but because of the heavier weight, the bus will carry its forward momentum, and again, all of that forward momentum that was there before will be carried away by the two particles afterwards. So we have them run into each other, boom, and you can see there the bus kind of bowled right through that, the fire truck bus bowled through that thing and just pushed it away. And again, if we had calculated the momentum before, it would be equal to the momentum afterwards. All right, one last thing. How is the conservation of momentum different than the conservation of energy? Well, there is a very, very big difference, and it's very important. That's why we learn about momentum separately. If we were to have an object like a car, like a vehicle, all right, and that car, all right, were to run into a tree, okay, so we're to run into a tree, that car would carry its kinetic energy, and it would lose that kinetic energy into many non-conservative forces. All right, we would have deformation of the car parts; they would be squished. We would have a lot of sound be produced. All right, there would be a lot of heat. All right, produced. Those forms of energy do not associate with motion, and therefore the motion of that car can, the kinetic energy of that car can be taken away. All right? But when it comes to momentum, there are no non-conservative forms of momentum. There is no heat momentum. There is no sound momentum. They're all forms of energy. So momentum is always motion. It's always dealing with moving objects. All right? And so when that car, with an initial momentum, all right, the initial momentum is running into the tree, where does its momentum go? Well, that momentum, if the tree does not move, is transmitted into the earth in which the tree is stuck to, and that earth will slowly, very slowly, lurch forward, so slowly that we wouldn't feel it because of the large mass of the earth, but that momentum would be transferred to a car-earth system, like a hit-and-stick problem. So because there is only one form of momentum, and it's associated with velocity, and we don't have non-conservative momentum, momentum is always conserved in an interaction, all right? And it's a very useful way to calculate collisions, all right? So let's say we have skateboard punk Reed here, all right? There he is. There's skateboard punk Reed, and if he were to run into, say, a tree or perhaps a fire truck, the momentum would be conserved, but perhaps he may come out a little damaged. His energy definitely would not necessarily be conserved, and some of that energy could go to injure skateboard punk Reed. So I'm not going to have him get injured at this point in time. All right. Hopefully that's some good information for what you need. and I'll be back next week, and I may even have another one tomorrow for conservation of momentum in 2 dimensions. We'll see what kind of a mood I'm in, see how this works. Alright, I gotta figure out how to shut this off. Here we go, I'm new at this.